Okay, hello everyone. So today we are starting a new topic: light, reflection and refraction. What is reflection? It's bouncing off of light from some surface. Light strikes some surface, comes back to the original direction, original side. That's reflection. Refraction is when light hits some medium and enters the second medium. Not the returning part, but what that goes into the new medium. That's refraction. So we go into details. We talk about electromagnetic radiation in the previous discussion. Light is also a type of a visible light is electromagnetic radiation. So we know the general properties like how to produce EM radiation, things like frequency, wavelength, the speed or the velocity. So we talk about those things. Now we are particularly focusing on just the visible range of electromagnetic spectrum. We call it just light or visible light, and we're going to talk about properties in detail. So this diagram on the PowerPoint is also, you can see, it's the reflection of light. There's a lake, there's some trees, you can see the sun. What is the real part? What is the reflection in this image? It's something to think about. You might be able to find the answer later, or you can give a try. Alright, so let's go and see what we have. So the topics we're going to discuss are ray model of light. Now again, previously we talked about this. When a source emits electromagnetic radiation, it pretty much emits in 3D in all directions. To represent these waves, outgoing waves, we use something called like the ray, like a straight line to represent this outgoing wave. So for an example, let's say here we have a light bulb and it emits light. These are actually like circles of waveforms going out from this source. Now moving outward in 3D, I will explain this in class as well. So we connect these peaks of each consecutive waves using a straight line, like this. And this we call a light ray, or sometimes we call it a beam. So from now on, for all our diagrams, call them ray diagrams, we will use these straight lines with an arrow, right? Because it's easy to manage, much simpler to understand. So we're going to talk about this ray model of light. Reflection, image formation by a plane mirror, spherical mirrors, index of refraction. It's about how light changes the direction, how it bends when it goes through different medium. Refraction, Snell's law, explaining refraction. Visible spectrum, total internal reflection, and spherical surfaces. So that's lenses. Alright. Okay, so let's move on. How do we see things? Like, what is the procedure of seeing something? Let's say you're looking at this pencil, right? It's on the table, so it's here. Let's say this is the pencil. And here's you, nose and eyes, ears maybe, mouth. Alright, what is the process of seeing something? First of all, there has to be some light. Now if this is a pencil and it doesn't have its own light, right, so there has to be some light in the room. Let's say there's a light bulb. So the light bulb emits light, and it emits light in all directions. So some of the light will fall on this pencil and they reflect, right? This incoming light reflect. It can reflect in all sort of directions like this. And some of these light, I mean, we are talking about millions of light rays, right? Continuous spread of light. Some of this light comes to your eye. Yes, and it comes to your eye. That creates a sensation of vision. Like light goes into your eye. The eye is also a very interesting optical instrument. There's a lens inside. It focuses this incoming light into the back of your eye, where you have all these light sensitive cells. We call them rod cells and cone cells. Rods and cones. Yeah. So these cells, the visible light, this incoming radiation, even though we use straight lines, they're like the radiation coming in, have certain frequencies, certain wavelengths, lambdas. Our eye respond to wavelengths in nanometers, like probably like I would say 300 to 900 nanometer range. So when this radiation hit these light responsive cells, rods and cones, they generate the tiny electrical pulses that go through the nerve system, goes to the brain, and creates this sensation of vision, like you're seeing something. So we'll get into details later. Alright? So basically what you need is you have to have a light source. The light needs to reflect, needs to reach your eye. So let's see a little bit more details. Image formation by a plane mirror. So this is the simplest case. Now if you go back to this example, here we have an object. It reflects light. So the incoming light, denoted by these arrows, they hit this surface. It's a reflective surface, and then here comes the reflected light. Right? So this is called the incident light. Incident. This is reflected. So you have incident light, it's the surface, get reflected. So let's talk about this process right here in detail. So here we have a plane surface. So I'm going to draw it here. And usually we call these mirrors. Like it's not just the mirror that in your bathroom or dressing table. A surface that can reflect light, we generally call it a mirror. And there's a standard that we draw lines on the back side of the mirror so that we know this is the front side. This is the front, this is the back. Okay, so here we have incoming light. So let's say it comes in. Incident light, right? Incident, the incoming. Wherever light strikes the mirror, that point we draw a perpendicular line. Oops, it has to be a straight line. This line, we call this the normal. It needs to be normal to the surface, the mirror surface. So there has to be 90 degree over here. Right? All our measurements are done from the normal. We make all the measurements, all the angle measurements from the normal, not from the mirror. That is the standard. Right? Alright, so we have the normal, we have the incident light, and here we go the reflected light. this angle, this incident light makes with the normal, this angle right here, theta. This is theta I, the incident angle or angle of incidence. The angle over here, theta R, the one that makes with the reflected light and the normal, this is the reflected angle or angle of reflection. Now it's very important to know that in reflection, when light reflects, theta I and theta R are equal. Incident and reflected angles are always equal. Okay, so that is something really important. Law of reflection, the angle of reflection equals to the angle of incidence. Pretty simple and also very important. So, for an example, here's a mirror, here's the normal, here comes, doesn't need to come from the left side all the time, it can come from the right side. If it makes 60 degrees here, it reflects with 60 degrees. Okay? It can be this way also. If it comes with 45 degrees, reflects with 45 degrees. Alright, reflection. When light reflects from a rough surface, the law of reflection still holds, but the angle of incidence varies. This is called the diffuse reflection. Here you see this is not a very smooth surface. Mostly the reflective surfaces or surfaces we see around us mostly are like this. There are a lot of, even if it looks like a very smooth flat surface, there are microscopic bumps, unevenness. So here we see a parallel beam of light coming in. If it is a very smooth surface, it should reflect parallelly. But because of this unevenness, from point to point, the incident angle changes, so the reflection changes, right? So they reflect in random direction. This is called diffuse reflection. This is a good thing or a bad thing? What do you think? It depends. I mean, think about you're looking at a tree outside the window. You see the tree because it reflects light. It reflects the light from the sun, right? I mean, pretty much, even if you walk away from there to a different place and look at the tree, you can still see it, right? Or different people standing at different places can see the tree because of diffuse reflection, because it reflects light in every direction. If it is only reflects very smoothly, whatever the light comes in will go in only in one direction. So you have to be at that spot to see it, right? Like surfaces around us, like the walls, the ceiling, a lot of things like wall hangings, everything has diffuse reflection. So here's one more example, diffuse reflection. Regardless of where you are still able to see some light. Over here, this is called what? Specular reflection. Very much parallel reflection. So you have to be at a specific point to see the outgoing light. They both have their own applications. Optical instruments need sometimes specular reflection. In nature, a lot of time what we have is diffuse reflection. Here's another example. Think about you're driving on the highway in the night. So, here's the road. This is you. You're driving. Going this way. And here's a vehicle on the other side of the lane coming towards you. As the light beams on, because it's a night, so the light, mostly a parallel beam of light coming out, and reflects. So some of this light coming to you, and because of that you can see this incoming vehicle, right? Because it reflects. Some of this light will go in different directions, like this. Let's say it's a diffuse reflection because there's so many unevenness on the road. It's not a smooth surface. Now I'm gonna draw a magnified diagram here. Here's the road surface. Let's say now it's raining. Like little after the rain. So it had rained some time ago, right? So now there's a nice smooth surface of water on top of the road. Now what happens? Light comes in, reflects. This is a specular reflection. Reflects parallelly. So if you are not in this area to see this, if you are not in the range to see this light, you might not even see the light. But once you are in the range, once this light comes to you, all the light is coming to you directly. So it increases the brightness. So that there is a reason that is, sometimes it's difficult to drive in the night because the light can be too bright. And it can be a little spotty, like not very continuous. Okay, alright. So let's move on. So here's an example. Give it a try. Light comes in with an angle of 15. Now this angle here is marked between the light and the mirror surface. So you need to draw the perpendicular, the normal, measure that angle. Think about the reflection, and then it hits the second mirror and then it reflects back. The question is, what angle will the outgoing beam make with the second mirror? So I'll leave it as a question for you guys. Okay, give it a try. Actually, I'll give you the answer. You work that problem. The answer, I think, is 75 degrees. Alright, give it a try. Image formation by plane mirror. How do we see things in a mirror? Now, here we see the object, right? If you go back to this example, here we have a pencil and light from the pencil comes to your eye, so you see the object. Sometimes you can see things inside the mirror. Let me clear this. It's like, let's say this is a mirror, like a dressing table or something, and you are standing in front of it. So this is you. You can see yourself, your image inside it. Or if there's, let's say, some flowers in the room, you can see the image of the flower, or something like this. So you can see an image inside the mirror, right? You can actually, if you turn your head to the side, you will see the flower directly, but you can see it inside the mirror as well. So how do we see things inside the mirror? So that's what this diagram says. Now let's see how to understand this whole procedure here. So here we have a mirror. Let's say this is the back side. There is this little container like water bottle over here, and you are somewhere here. Right. So this is how we draw the eye in ray diagrams. Now light from every point of this water bottle, in fact it's actually the light that reflects from the water bottle. It could be the light from sun, it could be the light in the room. So light comes in, reflects, comes in, reflects in many directions. So likewise, that is, let's say, like you need to see the entire thing, so but we'll just focus on the top of the bottle and the bottom of the bottle. You can see these two places, we can assume that you can see the rest of it as well, right? So some light comes here, it's strike the mirror, reflects, goes to your eye. You have the sensation, okay, light from the top of the bottle is coming to your eye. So now this is not directly coming to you, right? It's a reflection. So your eye, what it does is it's gonna extend this light backward into the, it's like, it's not really, there's nothing going into the mirror. You feel like it is coming from this direction. So here's another light beam from the top, goes to your eye, get extended. Now this has to be straight line, so right, if you use a ruler you can do a much better job. The eye tends to extend this backwards into the mirror, because this is where you are looking at. You are not directly looking at the bottle, you are not looking at this way, right? You are looking at the mirror. So light comes to you, but you feel like it's coming from here. It's kind of an illusion. So where these dotted lines meet, that's where the top of the bottle appears. Same thing here. From the bottom of the bottle, light goes to the mirror, reflects to your eye, to the mirror, reflect to your eye will extend them backward. My diagram is super bad because I'm not using straight lines, not using a ruler, but where they meet is where the bottom of the bottle is. Okay, so that way we have a feeling, like an illusion, that there is an image inside the mirror. Things to think about, important things. For plane mirrors, the image that is inside the mirror, now this is the front of the mirror, this is the back of the mirror, right? So this is inside the mirror, this side, back of the mirror. This image is called a virtual image. Virtual, because it's not real, right? There is nothing real behind the mirror. It's just something you see, like it appears that there is something there. It's a virtual image. And we call these distances, so this is the object, this is the actual thing, so we call it the object. These distances, object distance, use DO, object distance, this distance, image distance, DI, they are equal. For plane mirrors, it's really important to remember, for plane mirrors, right over here, plane mirror, DI is equals to DO. Image distance is equals to the object distance. So if the object is 1 meter in front of the mirror, the image will appear, it's like it's 1 meter behind the mirror, right? It's upright. Means you won't see an upside down bottle here, something like this. There are certain mirrors that does this kind of images, we'll learn them later. But for a plane mirror, it's upright. And also, if you think about the height of the object, this height of the object and this height of the image, they are equal. So HI equals HO. In other words, no magnification. If the image is bigger than the object, if it appears bigger than the object, we say it's magnified. Sometimes image can be smaller than the actual object. That is also a magnification, but it's a negative magnification, right? But for plane mirrors, it doesn't make any magnification. Or you can say magnification is 1. So we define the magnification M as HI over HO, the ratio between the sizes of the two things, image and the object. This is equals to 1. Okay, let's see what else we have. called a virtual image, as light does not go through it. Distance of the image from the mirror is equal to the distance of the object from the mirror, so di equals do. Okay, here's a question for you. How tall must a full-length mirror be? A person, a woman, 1.6 meter tall, standing in front of a vertical plane mirror. What is the minimum height of the mirror, and how close must its lower end be to the floor? Okay. How big the mirror should be and where should we put it? If she is to be able to see her whole body. Assume her eyes are 10 centimeters below the top of her head. So all these things are important. Height of the person is 160. So from here, bottom to top of the head, 160 meters, 1.6 meters. And her eyes, and eyes are is what we need to see something. They're 10 centimeters below the top of the head. So here's the image on the right side. What is the minimum length of the mirror? I mean, you can put a huge mirror, you'll be able to see the whole figure, right? But what is the minimum? How small it can be? And where should we put it? How high from the ground? Okay, so try the ray diagram. Try and see what you can come up with. So I'll give you the answer. The mirror must be 80 centimeters high. Size of the mirror, the length of the mirror has to be 80 centimeters with its bottom 75 centimeters off the floor. Bottom edge. So over here should be 75 centimeters above the ground. Okay, so that's for you to work on. Here's that conceptual question. It's a photograph, the lake, there's some water, you see the sun here, there's a bunch of trees. Is this upright or is this upside down? Or is it right side up? So think about it. I won't give you the answer right now. Okay, so we are moving on to a new topic. So what we just discussed was reflection from plane mirrors. Pretty simple. You have a mirror, comes in. If it comes perpendicular to that, it's going to reflect the same path, perpendicular, right? If it comes with an angle, it's going to reflect with the same angle. And then it makes all these images and the image properties we talk about. They have to have the same distance in front of it and behind it. They have to have the same size, no magnification. It's virtual, means it's always behind the mirror. What I meant by that, you have a mirror and you have a bottle over here. You won't see an image of the bottle in front of it, right? This doesn't happen. It's always behind with the same distance. We normally use dotted lines to indicate the image. And also from now on, whenever we talk about objects, it can be anything. It can be a bottle, it can be a person, it can be a tree. We just use an arrow, an upright arrow, to indicate the object. So the height of the arrow is the height of the object, and the arrow head tells you the orientation. So this is upright. So this is like this bottle. Okay. So in this case, it has to be an arrow to the height of the bottle. Alright. Let's move on to spherical mirrors. Formation of images by spherical mirrors. Spherical mirrors are shaped like sections of a sphere and may be reflective on either the inside or outside, concave or convex. This kind of shape. So here's a piece of a circle, spherical shape. Like let's say we have some piece of glass produced to have this kind of spherical shape, and then you apply a reflecting medium in the back. So this is the front, this is the back. So these kind of mirrors are called concave. It's like caved in, concave. This one is the reflective surface. So this is the front. This is where the light comes in. This is where the light comes in, and it reflects to the same side. These kind of ones, like bulging outwards, that is the front side, convex. So we're going to talk about the properties of these mirrors. Now, to describe properties, we will use parallel light coming into the mirror, right? Parallel light. Now we know that if you have a light bulb, light goes in all directions like this, so it's not really parallel. But if you consider some light far away, like over here, a couple of meters away, these beams, light rays, appear to be much more parallel when you are far away from it. Think about the sun, billion kilometers away from us. Even though it emits in every direction, the light that comes to us on Earth pretty much parallel. For our purpose, it's parallel enough. Like in this diagram here. So light reflects from this tree, comes to you, it's mostly parallel. Okay, so before that, let's talk about some properties. We'll start with a concave mirror. So here we have a concave mirror. Whenever we talk about ray diagrams, we draw something called the principal axis, a line that goes through the center of the mirror, and that spot it has to be perpendicular to the mirror, right? So this is our central axis. And for all our measurements, we draw a line behind the mirror. You don't have to actually draw it, but we make all the measurements from this point, the midpoint of the mirror, right? Light that comes parallel to the central axis, parallel light, reflects and goes through a point in front of the mirror. Now the light reflects, right? It goes back to the same direction. Coming from the left side, it goes to the left side. Parallel light, all that parallel light, if this is a good mirror, they all go to the same point. It's from the mirror geometry. Comes parallel, goes through this same point. This point is called the focal point. Or focus. F. We use the letter F to indicate that. This point over here. So if it is a good spherical mirror, all this parallel light will go through that same spot. Previous diagram, what it shows is, if the curvature is not that good, they won't come to the same focus. This is a condition in mirrors. It's called aberration. So this is a problem with reflective surfaces. Telescopes can have these problems. When you build huge telescopes, it's difficult to reflective telescopes. It's difficult to have a good sharp focal point. That is something happened with the Hubble telescope. If you have heard about this gigantic reflective telescope that orbiting the Earth, when it was sent to the orbit in 1994, I guess, it has an aberration issue. So it was like $1 billion telescope, so NASA didn't want to abandon it. So they trained a team of scientists to fix it in space, because you can't bring it back. It's too expensive to bring it back. So they went up there did some spacewalk outside, they fixed the issue, and I mean, it's one of the best we have now, giving us magnificent images. But yeah, this is aberration. So going back to the topic, the light that comes parallel to the mirror, to a spherical mirror, to a concave mirror, reflects and it goes through a single point. Remember, parallel light, not every light, but the parallel light. That point is called the focal point. That distance from this center point of the mirror to the focal point, f, that is also f, this is focal length. Another interesting thing is, now these mirrors are part of big circles, right? So it's a big circle and this part is the mirror. So the circle has a radius. This distance, the radius, now this is that mirror piece. This distance, the radius of it, and the center point, we call it C. Actually, the focal point is half of that. Focal point is here. So if you have a mirror like this, and if the focal point is here, the center of this curve, we call it the radius of curvature. Or you can just say the center. This center, this distance is twice the focal length. So here it shows that this focal length is half of the radius. This length, the distance to the center point is the radius. The focal length is half of that. Alright, so we're gonna learn how to draw images with spherical mirrors. So we're gonna start with concave. We use ray diagrams. We're gonna consider three very significant light rays, right? So let's draw the principal axis. Here's the mirror. A ray parallel to the axis, I'm talking about point 1, a ray parallel to the axis, after reflection, it passes through the focal point. So that is, so let's say here we have an object. This is the object, right? So this distance from this point to the center of the mirror, that's the object distance. So this object is emitting light in all directions. It's emitting means it's reflecting. Let's say that there's light coming from this object. So from the top, from the bottom, throughout the body, light is emitting. Let's just focus on light comes from the top of this arrow, right? So that also goes in any direction. We're gonna consider just one light ray that goes parallel to the principal axis, and we know that if this is the focal point, it's gonna go through this focal point. So this is one of the light rays we're going to use to find out where the image is. So that's number 1. The ray through the focal point after reflection, it is parallel to the axis. So one of these, another light ray can go through the focal point directly from here through the focal point. So it's going like this. Again, use the rulers. One that goes through the focal point reflects parallel. And when two light beams meet, two light rays meet at that point, that's where the image is. Now here's the head. This light is coming from the head of this object, right? So the head appears here. Actually, it's going to be upside down, like this. This is the image. You can use a third one. A ray perpendicular to the mirror reflects back on itself. So I'm drawing a new diagram to show that. let's say here's an object, and the light from this object goes perpendicular, it reflects along the same path. So we can use any two of these three, or you can use all three. At least you need two different lights. One that, it's easy to use this, the one that goes parallel and one that goes through F. The parallel one reflects through F, the one that goes through F reflects parallel, and where they meet is the image formation. The image will be formed there. So here's those diagrams one more time. Here's the object. Now this time we have placed it between the center and the focal point. Right, so we will draw a couple of diagrams in class. Goes parallel, reflect through F. The second one, number 2 here, goes through F, reflects parallel, and where they meet, this is where the image is going to be. Number 3, one that goes perpendicular, number 3, perpendicular to the mirror surface. Actually, if something to be perpendicular to the surface, this comes from geometry of circles, right? It has to go through the center. Anything that goes through the center, you draw a line going through the center, that becomes perpendicular to the surface, to the circumference. So the light that appears like coming through C, is number 3, will reflect along the same line. They all meet at the same spot. Here we have the image. Intersection of these 3 rays gives the position of the image that, alright, you guys can go ahead and read. Okay, so here's an exercise. Going over time here. Here's an exercise. I want you to try this. Let's say you have a concave mirror with F equals 3 centimeters. So you can draw a diagram and make sure to use rulers. Now, please bring rulers to the class. If you're coming in person, I can give you. Keep a ruler handy when you do the lecture, because we need to measure these, to make these measurements. So here's a concave mirror. I'm going to place an object at DO equals 8 centimeters. Object distance is 8 centimeters. So it's like this. F is here, your object is over here. I want you to draw the ray diagram and figure out where the image is. Okay, so draw these things according to a scale. Try these different places, 8 centimeters, 5 centimeters. Okay, try these two. Alright, thanks everyone. We will continue to the next video soon. Okay.